to hear about their concerns and fears. And then we also wanted to look and see were there other partners that we could identify during the planning process that we could bring on board later down the road. So ultimately, a plan with goals and recommended specific activities to be accomplished has been finalized, and we can commend the board for their efforts. As you will note in these goals, and they are on the other side of that plan we hand out. Our first goal is to increase people's awareness and understanding of the individual connections and efforts within the watershed. And I remember very specifically at a board meeting that the board talking about, they really thought educating the residents of the watershed, the landowners, producers, that was really probably one of the most important things that we could be doing in the future. Our second goal is to improve water quality in the watershed. Third, to reduce the effects associated with altered hydrology. We have a lot of heavy flows and diminished base flows within the watershed. Increase the habitat and plant life in the watershed. Create an understanding of the recreational opportunities in the watershed. We actually have pictures from quite a long time ago where people were fishing in the Squaw Creek and maybe thinking about how we could restore that. And then lastly, to work cooperatively with identified stakeholders and resources and facilitate partnerships to implement the watershed plan. So as you can see from these goals, the Watershed Management Authority Board was very committed to educating, communicating, and building cooperation within our watershed. And I'd like to kind of just leave you, before I turn this over to Jason, just thinking about, sometimes I think about a triangle or a three-legged stool as you're doing your work. But I think if any one of these pieces had not been working together, it would have been very difficult. But the board was very open, they were very collaborative, they were very communicating. They were learning as the analysis was being done. The not-for-profit was really bringing the best of what we could do to educate and promote and engage. And then EOR was bringing all their technical skills and really serving that piece, but really we ended up being kind of a complete team. So that was really great. And I think I did I'll pass this around, but we do have several plans down on our booth, but you might want to look through it, and we have extra copies I can always send to you. So with that, I'm going to turn this over to Jason, who's going to go over the technical pieces that we have.
Morning. So I'm going to go through kind of the fun, nerdy aspects of this project. Penny mentioned this really a formal document that's being passed around now that has a lot of effort was put into crunching numbers and did a very useful planning deliverables. And what I dealt with specifically was once we set the stage in terms of where Squaw Creek is right now, the current state of the watershed and the reduction goals, what are some of the things that we can do? What would be an implementation plan? What are some different strategies that we can implement, particularly in the ag areas? And what would it look like? And what kind of reduction in costs would we expect to come out of those? And so we went through a series of steps here to kind of do that. First, some quick acknowledgments. Our funders here, working with the Squaw Creek Watershed Management Authority was great. Several folks are here. Paul Toots here. Use my little pointer here. Herb Class is here. These guys are just great advocates and just sort of handed it over to us from the beginning. And we checked in with them a lot. And I think it was a very great collaborative effort, as Emmons pointed out. We had some folks sort of outside the sphere a little bit that helped a ton. A couple of those folks are here too as well. We'll get down to the Iowa State folks that provided insight, some technical assistance, a lot of GIS files. And last, folks at the USDA and Ames, in particular Sarah Porter and David James, they work on a team that has developed a set of novel tools in support of something they call the Torber Framework from Mark Torber that's also in Ames. And I'm going to go through this in greater detail. But this was a huge group effort, and a lot of people gave us help along the way. So I want to acknowledge that. So really quick, what that plan that's being passed around is basically trying to summarize is overall, how we compiled all the data, how we determined what the current state of the watershed was. We were crunching through all the data that's available in the watershed. There's quite a bit of it. We were looking at what has been done in terms of channel stability assessments. There's been a lot of that as well. We also wanted to catalog what's going on right now in terms of crop rotations and fertilizer practices in the watershed, so that we could, when it comes time for modeling, make sure that we're representing the spatial distribution and just how the practices are laid out across the watershed right now, what the current thinking is, what the current cultural practices are. Ultimately, a source assessment of the pollutants from an observed data side was done, and that's, again, these things are a big part of what the watershed management plan is showing. Last, what I'm going to talk about was really the last part of the watershed management plan that deals with how do we change things, what are some different ways that we can strategize and plan, particularly using BMPs, agricultural BMPs. So a little bit of background, Penny laid it out. If folks aren't from around here, we're right at the epicenter of the talk here. We're in Squaw Creek. It's a huck and up here, part of the greater stump system. This is off the slide a little bit, but it's also unique in that there's a highly agricultural area in the upper reaches of the watershed, and Ames is right at the end. So we're right in the middle of this. What our data analysis and how we laid the foundation for the BMP strategies, what we found out here, when we look through here, it's made up of 7 Huck 12 watersheds, and those are over on the right side of the screen. 150,000 acres. It's mostly all corn and soybean, and of that, 70% of the ag acres were estimated to be drain tile. So that's an important consideration. Overall, the nitrate is high at about 6.5 milligrams per liter on average. The ortho-P is 0.3 milligrams per liter, which is actually very high. So in terms of trying to generate some goals, here we followed the Iowa's state nutrient reduction plan, which will call for a 29% reduction in phosphorus, 41% in nitrogen, and a little bit more of a soft target for trying to double soil organic matters to attain increased soil health, which is been getting a lot of emphasis lately. So in terms of the planning, how we laid out the BMPs, we probably get sick of seeing this graphic, but this is how we laid it out. In terms of prioritization, this is what we're trying to find where the hot spots are. There's a lot of different tools you can use for this. I put down a few examples as we go through watershed to do some of these things. Sometimes there are models that exist in the watershed that you can rely upon. Sometimes there's a lot of overlapping data that you can rely upon. In this case, we built actually a Squaw model, which is a heavily agriculturally focused watershed model, and it has explicit support for agricultural practices and drain tile, which is very, very helpful in this watershed. There are other lines of data that we can use as well here, and we did. There have been some sediment studies that have been done in GIS, I think through Iowa State. So in general, as we look at this approach being able to maybe be applied to other places, lots of overlapping capabilities are good because you like a weighted evidence approach in terms of deciding where to concentrate your efforts, because most models in and of themselves can be wrong, so it's better to have more. Targeting here, specifically, we're talking about targeting sort of where are the actual potential opportunities to place BMPs at the field scale. So look at a map and say, here is a candidate spot for BMP. So for this, we've got an array of different BMPs, in-field ones that just deal with nutrient management and optimized nutrient management, different tillage approaches, more emerging technologies like cover crops, and then these edge-of-field BMPs that we got here that I'm calling terrain dependent, meaning that they have a big GIS component because their upstream drainage area that flows to them is going to be a huge indicator in terms of what kind of return you're going to get on the investment. Mostly because you want a lot of drainage area flowing into the BMP so that you're actually optimizing its efficiency and putting it in a place where it's going to do the most good. So to do this, and I'm going to mention this over and over again, we use what we're going to call the Torber Framework, and I think I see Mark out there, so thank you in advance. I probably said his name more than last year than I have my own. It's really an innovative approach. It's based on, I'll go into much more detail here, but it's basically an innovative approach. It's a governing set of principles here that really is meant, looking at this pyramid to say, build your soil health, start from the ground up, and sort of take a treatment train approach in terms of saying, get your soil health fixed, move up the chain from infield to edge of field, and chip away a little bit here and a little bit there, and you're going to get, the thought is the whole is going to be greater than the sum of the parts in terms of your BMP plans by using by using this framework. It's also backed up by a very novel set of GIS tools that I'll show you later on. They're pretty cool. So as we go down the chain here, we also need to have an idea of what we can expect for outcomes. So if we're going to know some costs, we're going to put some BMPs down. It'd be nice to know just exactly what kind of reductions we'd like to expect. So I generally end up using results from models, but values from literature are very good, and there was a great meta-analysis that was done, as folks probably know, as part of the nutrient study. Several folks in the audience here were instrumental in putting that together. So instead of trying to get SWOT to do things I wanted it to do, I just relied on the literature values, which are much better in this case. There are different cost mechanisms, or different cost funding mechanisms, cost share mechanisms. We use EQUIP for our estimates. This is sort of a snapshot plan to try to determine, at least get an estimate of what's realistic costs and cost effectiveness. So all this in theory is going to build an implementation plan, which is going to consist of, or does consist of, a number of scenarios, some output maps, and then it gets down to the reductions of costs and what the ultimate cost effectiveness is. So it gives some different example scenarios. So first we'll go back to the prioritization and look at what SWOT spit out. So we constrained the SWOT model so it would take into account tile and where the distribution of where the current crop management practices were, where the manure was. And sort of the takeaways from this, first of all, the primary factors, there's no great hocus pocus in terms of what SWOT's spitting out. It's really a factor of where the tile was, where it wasn't. To what extent in any tile field there was depressional volume, whether that was drained or not drained, and then whether we had manured or non-manured systems in terms of how the fertilizer was being delivered. The takeaways in terms of the important conclusions over this side were, not surprisingly, 85%, we estimate 85% of the total watershed end budget was coming out of the tile areas, tile row crop areas. And like most watersheds, about 35, say 30, well, about a third to a half of the total NP and sediment was coming from a relatively small part of the watershed, about 20%. So the thought was here, this is a local watershed approach, but at least gives us a little bit of a guide as a first step to say where are the priority areas. It's split up into about 100 small watersheds. And I'll just backtrack here a little bit. These are just ranked scales. It's all relative, high, medium, low. It wasn't designed to generate exacting predictions. It was just trying to give a range. So here's the Torber Framework. The pyramid that you've already seen, it's attached to like I said, a novel set of principles here, and actually naming the BMPs, actually showing the BMPs and which ones work in particular situations, how they can work in concert with each other, and how you should try to prioritize their use in the landscape. And so I didn't highlight the ones that we used, but we took a snapshot. So he suggests a lot of different BMPs here. I'll show you which ones we concentrated on. We tried to concentrate on the ones that were giving us the best bang for the buck. So those that actually dealt with both nitrogen and phosphorus for this study. So in two of those that we concentrate on were what I'm calling restored wetlands, but what the framework calls nutrient removal wetlands, and riparian buffers. And these are direct outputs from the set of GIS tools that I mentioned support the Torber Framework. And so we've zoomed in on a Huck 12 here in the central areas of Montgomery Creek. And what we're seeing here in the restored wetlands, this is what GIS is spitting out of this LiDAR analysis, are drainage areas here, and the green spots are the actual surface area of the candidate basin. So these would be existing depressions already in the landscape with their drainage areas already demarcated and represented in LiDAR to say, here are areas in which you've got drainage area already flowing to existing depressions or depressions that could be easily modifiable to hold water. And a huge thing too here is it is encapsulated in research that folks here down in Iowa have done, Bill Crumpton and others, that look at the ratios between the wetland pool area, that nominal area, and the drainage area flowing to it, so that you can maximize your denitrification. So in cases where the pools might be too deep for denitrification, those would be good sediment basin candidates. So here we concentrate on these restored wetlands. The buffers, there's a huge amount of potential with the buffer sites, as they can be surface water-driven sites that are intercepting sediment flowing through them, or they can have subsurface component where you're actually getting a lot of water running to the subsurface and getting a lot of denitrifications. Those are also areas where folks have heard of that would be candidate sites for century buffers. So what the tool set spit out here are different flavors of buffer sites. So in areas where you're going to get a subsurface flow path, in areas where you're going to get a surface flow path, where you're going to get both, or where you're going to get neither, and really the only thing it's doing is still useful, but it's maybe not intercepting a lot of drainage area, but it is stabilizing stream banks. So this gives you a map of the candidate sites for these and the drainage areas flowing to them. And so what we did across the entire watershed, we took these, we concentrated these two, but also we did several others like grass waterways, controlled drainage, some others. We concentrated on these. We took these drainage areas that the GIS analysis spit out, and we use this, we forced this into the framework in terms of trying to do an aggregate accounting of what a BMP plan would entail. So actually taking opportunity, instead of saying in this watershed, we would like to clean this up by a certain amount and saying, to do that, based on literature, we would need 10 wetlands, for instance. We can actually see here what is actually practical in terms of what the landscape can actually support. Where the smart areas to put it would be if you could only put in a mile buffer, where would you put it? This map would give at least a nice snapshot of where to start a road. It all needs to be field validated by folks walking it, but it's a huge advantage over what we would have previously had if we were just going to start hitting the ground looking for spots. So to get to the predicted outcomes and the cost and funding, again, we relied on the nutrient strategy here. And so there's actually better graphics, I think, in the nutrients strategy. And but we reformulated this here, and we got the N and we got the P reduction per acre on average. We assessed the cost, and we kind of came up with a cost effectiveness index here, where negative values mean that it doesn't cost anything, positive values mean it does. The takeaways here for these different categories, we got efficient, N and P application. There are a number of different things that we've done. Generally, they're free or profitable, meaning those efficiencies actually help either don't hurt the crops at all in most cases, but they also eliminate the need to put down as much fertilizer as we put down. These more emerging ones here, the only reason I mentioned the cover crops and the reduced tillage is the assumption here was if you put in rye cover crops and use no-till, it actually increase your soil organic matter health over time. So these were put in as sort of a longer-term soft target. Land use change to perennials is extremely effective if you look at the reduction. But they're fairly expensive. Here, these end-of-field ones, these would be the ones that would be directly supported by the Torber set of GIS tools. Again, we concentrated on the wetlands and the riparian buffers. They do a good job of treating both, and that's why we concentrated on them. We're getting a large reduction per acre for both N and P. So if we put all these things together and spit out an example scenario, again, I list a number of different ones that we tried out here, but we concentrated on these two. And we look at what this gives us. What this is trying to tell us is what does it take to reach these goals of reduction goals of 41% and 29%. Just how much of the watershed do we have to put in some level of BMP? Would these things be put in parallel, or would they be put in serial? How would it work? What would the plan look like, and what would it cost? So it's just a benchmark. Well, what this is telling us in our analysis is about 20 to 40% of the total ag acres in Squaw Creek would have to be put into some level of BMP. This would include 40%, and I would say a meager 40% of the more efficient N and P application. Again, these things are assumed to be free. They would necessitate a cultural change, but they should be put everywhere. But we took a conservative approach and said 40%. We would put 20 in cover crops with no-till to build the organic matter health. We would put 40%. 40% would run through either a nutrient removal wetland or a buffer. And even though they're expensive, there's an interest in trying to see what we can do with the perennials, whether this is through the strips program or not. So we put 10% in there. It's rather expensive. If the thought was let's put this in just and see what this gets us. So these are not. If we add down through here, we get a total reduction of 43% for nitrogen, which hits the 41% target, 41% for phosphorus, which exceeds the target. And these are not, I didn't just add down the line. I actually attempt to serially throw these on a watershed. So we're not just adding up the reductions cumulatively. We're actually taking a more conservative approach and saying, if we reduce this much, there's only this much left, how much we flow to the next BMP, and so on, and try to see what the serial effectiveness would be. So the other thing is, the cost is, depending on who you look at, is significant. It assumes a 20-year commitment, and it comes up to be about $23 per treated acre. And just as a quick context, I think corn and soy profits, maybe not this year, but are somewhere around the 260 to 340 range. So it just gives you some context around what the cost would be. This is after cost shares, and just how that fits into the overall economics of the current farming practices. So I think I'm almost out of time. We put this up too to show that what this continuum is, it shows where nitrogen and phosphorus are right now, and it shows what the eclipse region average is, what some different criteria, and what some different benchmarks and targets are, and just where this strategy, where the nutrient strategy gets us. And so it gets us far, but it doesn't get us to some of these other areas like Minnesota's DP standards is a little more stringent. It's not that anybody's making that there either, but depending. So what this is saying is that there's a significant reduction, but there's probably a little bit more work to do there. So, but it serves as a good starting point. It's a good exercise. And with that, I'll get some questions. Thank you.
Yeah, partly I missed your prioritization section on there, but I was wondering, LiDAR has been really wonderful. And I know a lot of these others were installed pre-LiDAR, and actually look at some that were installed with 30 meter DEM. And it looked like, well, it should intercept the flow. I mean, everything looked uniform, and with LiDAR and ground truthing, it completely bypassed buffers or the concentrated flow to it. Did you see any photos like that?
Well, we weren't able to go through an actual ground truth. So these were LiDAR derived ones, and I didn't do a quick comparison to what the 30 meter would spit out. The assumption is it's better, but the data, the LiDAR was hydro-corrected, which would at least try to get at whatever channels that actually exist out in those fields, to some degree if they're visible with aerial photography. But there's no question there might be some areas where there's a stream blowing through there, and it wouldn't be a good spot. Here, the thought is you're trying to optimize and try to get to, assume that you're going to get a little bit of sheet flowing through there, but you don't know for sure until you go there.
Now that you have the assessment and the planning done, what are going to be your biggest challenges to actually implementing the practices on the ground?
With my own experience, really in south central Minnesota, but on the same sort of soil as they're here, the same kind of farm culture, is that you can put up as many of these maps as you want, but it really comes down to the individual landowners to say what they're interested in actually doing it. So there's a social science aspect of this. Certainly there's a funding aspect of this. We saw it's not cheap. So I mean, trying to kind of take the maps and meet the social science side, I think, certainly these maps can be taken out to the landowners and say, here are some opportunities. Some of it would just be how it's communicated to them. Here's some potential opportunities in your field or your 160 acres. And it may work or it may not, but certainly there we have to sort of bring the two technologies together. My sort of cubicle analysis needs to be brought in sort of real world connections with farmers. That's one distinct challenge.
Yeah, I find it very encouraging to see that you're looking at kind of the longer range, the 20-year framework, I think I heard you say, and setting out kind of some benchmarks, because I think it can be kind of overwhelming when you look at what the magnitude of change is needed, but if you break it up into a longer period of time and you have some funding, it'd be nice if we had a more sustainable source of funding, but it's good
Kind
to
of
see.
take it in chunks.
Just a comment.
Yeah, no,
One more quick question.
okay.
Does your cost per acre assume cost share for every practice?
It did, which is roughly ends up being about 50%. So the $23 an acre should have been, because our estimate of the farm cost. That's right. So in some cases, there's a big installation at the beginning, depending on the practice, and we're spreading that out. That may not be the way it would actually be paid. So it's, in that sense, we're being a little conservative there. But
Well, thank you very much.